Today we start Chapter 5. Chapter 5 starts Test 3. Okay? Now, in Chapter 5, we're going to be concentrating in on covalent compounds. And we're going to be looking at covalent compounds in more detail and looking at going from their formula to their molecular three-dimensional structure. And by looking at their three-dimensional structure, we're going to learn something about the behavior of that molecule, which tells us about the chemical properties and the physical properties of that compound. So, we know when we're dealing with covalent compounds, two atoms share electrons. Okay? And in most cases, when they share electrons, they do not share those electrons equally. The nuclei of the two electrons are different sizes, and they're going to be different distances from the shared pairs of electrons. That means there's going to be different interactions between the nuclei and the shared pair of electrons. Okay? So, if we think about looking at the molecule HF, hydrogen fluoride, and we look at the electric field of the molecule and how the molecule orients itself in an electric field, we'll see that the hydrogen end of the molecule is attracted to a negative plate and the fluorine end of the molecule is attracted to a positive plate. This means that the molecule is polar. That means that there's a separation of charge across the molecule. Now let's look at a pretty picture. Okay? Now here's HF molecules in an electric field. The green blob, the green end, that's your fluorine end. The white end, that's your chlorine end. So you can see when the electric field is on, they all orient themselves so that the hydrogen end is being attracted by the negative plate and the fluorine end is being attracted by the positive plate. So that means one end is slightly negative and one end is slightly positive. Okay? So that tells us that when atoms share electrons, there's a good chance that they're going to share those electrons unevenly. And when we have uneven sharing of electrons, we call it a polar covalent bond. Most covalent bonds are polar. Okay? There are some examples of non-polar equal sharing, but most are polar. Now, what this indicates to us is that in bonding, there are kind of extremes. We can think about pure covalent as being total equal sharing. We can think about ionic is electron transfer. And polar covalent is somewhere in between. Okay? So let me draw a picture for you. Just kind of get this set in your mind. So we have pure covalent, equal sharing. We have ionic, which is electron transfer. And somewhere here in the middle, we have polar covalent, which is unequal sharing of electrons. Okay? So if we're looking from pure covalent to ionic, I want you to think about the fact that there's kind of a smear going from one to the other. Okay? Now, the way that we judge the unequalness of the sharing of electrons between two atoms is through using something called electronegativity. Okay? EN is our abbreviation for electronegativity. It's the ability of an atom to attract electrons to itself in a chemical bond. Okay? Now, here's our electronegativity table. Notice that as we go up a family, electronegativity increases. And as we go from left to right, the electronegativity increases. Now this makes good sense because remember the atoms up here in this upper right-hand corner, there are small atoms, okay, with their electrons held very tightly. Any new electrons that it interacts with is in pretty close to the nucleus. And that distance from the nucleus is really important to how the nucleus is going to interact with the electrons that it's reaching out for. Okay? In fact, it happens as a factor of r squared. So the smaller it is, you can kind of quadruple. You know, if it's half the distance, you quadruple the attraction. Okay? So the most electronegative element on the periodic table is fluorine. The least electronegative element is over here with francium and cesium. Okay? Big atoms. So we can see that if I bring an oxygen and a fluorine together, they have different electronegativities. They're going to have unequal sharing. If I bring a nitrogen and a chlorine together, though, they both have an electronegativity of 3. They're going to equally share electrons. So we can use electronegativities to help us judge how unequal the sharing is. Okay, scroll up for me. Okay? So, the most electronegative, I've already told you that. We consider something to be pure covalent if the difference in electronegativity between the two atoms is less than 0.4. We consider it to be polar covalent if the difference is greater than 0.4 but less than 2, and ionic if it's greater than 2. Now, there are some things that don't fit very neatly into this kind of scheme. This is kind of a rule of thumb thing. It says this is approximate, but we always look at other factors. Okay? So, pure covalent, polar covalent, ionic. So you can see between 0 and 0.4, between 0.4 and 2, and greater than 2, ionic. Okay? So, to quantify the polarity of the bond, we can use something called dipole moment. Now, if you get up and you take a 400 level physical science class, you'll talk about dipole moment quite a bit. It's the magnitude of the charge times its separation. Okay? And the percent ionic character is based on the measured dipole moment divided by the dipole moment if the electrons were transferred. It's a lot of math. Don't worry, I'm not going to make you do it. Scroll on up for me. Okay, now here's a chart of some common diatomic compounds, di meaning 2, and their percent ionic character. If it's more than 50%, we consider it an ionic compound. So you see LiI, Ki, LiCl, Sc, cesium iodide, potassium bromide. I've got a metal and a nonmetal, all good ionic compounds. But notice that lithium bromide, okay, is down below the 50%, which tells us that even though it's a metal and a nonmetal, there may be some polar covalent characteristics to that bonding. HF is below. HCl, ICl, all of these guys, low percentages ionic character, so these guys are polar covalent. Okay, so it's another way to look at it. Okay, now let's look at practice problem 5.1 on page 209 in your textbook. Let me get there. I'll eventually get there. Okay. Here's practice 5.1. Now, it says, is the bond between each pair of atoms pure covalent, polar covalent, or ionic? Okay, so write those guys down. Let's start very simply. If I have two identical atoms bonded to each other, they've got the same electronegativity. So the difference in electronegativity is 0. So an iodine bonded with an iodine is going to be a pure covalent bond, totally equal sharing. Now let's look at cesium and bromine. And I'm going to write them down, CS and Br. Okay? All right, now I'm going to flip a page on us. Let's look at this. Scoot this down a little. You can see that cesium's electronegativity is 0.7. If we look at the other side, bromine is 2.8. So the difference in electronegativity is 2.1. Okay, guys? I've been writing this on the board. I know you've been in the dark, but there we go. The difference in electronegativity is greater than 2, so we consider this to be ionic. Okay? If we look at the next one there, the next two atoms that we're supposed to kind of pair up are phosphorus and oxygen. So let's look at phosphorus and oxygen. Okay? So let's look. We look at phosphorus, its electronegativity is 2.1. We look at oxygen, it's the second most electronegative element on the periodic table, 3.5. Okay? So, if we get the difference in electronegativity, I would have, let's see, 1.4. Now, the difference in electronegativity here is less than 2, is greater than 0.4, so this is polar covalent. If you get a mixed message, the difference in electronegativity says one thing, but the elements you're dealing with are another. Let's say I had a metal and a non-metal, and I got a difference in electronegativity that's less than 2. We'll still identify it as an ionic compound, but understand that it's probably got some sharing going on and not pure electron transfer. Okay? So you can watch out for things like that. All right, let's move on. So, now, if we're going to study covalent compounds, and we're going to look at the effects of the unequal sharing of the bonds, we're going to need to know something about the three-dimensional structure of the molecule. And to build the three-dimensional structure of the molecule, we need to start with a blueprint. Okay? Just like you would if you were to build a house. They start out with a flat drawing, and they expand it into, voila, a 3D house. Now, we're going to use the Lewis octet rule to help us determine the structure of molecules, and we're going to stick with simple molecules for right now, ones that have a single central atom. So one atom in the middle and atoms coming off of it, kind of like spokes on a wheel. Okay? So let's remind ourselves about the Lewis octet rule. Or I don't know, maybe I haven't discussed the Lewis octet rule with you yet. Lewis octet rule says that all atoms bond to achieve 8 valence electrons. That's an octet, except for hydrogen and helium, which only wants 2 valence electrons, a duet. Okay? Now, let's remember some things that we already know about how many bonds different atoms want to make. Specifically, we're going to concentrate in on nonmetals, because nonmetals are where we see covalent bonding. Okay? Now, let's look at the periodic table for a second. And let's flip over to remind ourselves of some things. Okay? There we go. Now, if you remember our Lewis dot symbols, neon has 8, fluorine has 7, oxygen has 6, nitrogen has 5, carbon has 4, boron has 3. Okay? Because this has 3 valence electrons, 4 valence electrons, 5 valence electrons, 6 valence electrons, 7 valence electrons, 8 valence electrons. So I'm going to draw their Lewis dot structures. Okay? The Lewis dot symbols are those elements, and we're going to talk about how many bonds they can make. So, boron, carbon, nitrogen, oxygen, fluorine, neon. Okay? This has 3 valence electrons, 4 valence electrons, 5, 6 valence electrons, 7 valence electrons, 8 valence electrons. Now, Lewis's dot symbols place 1 electron on each side of the atom. 1, 2, 3. Okay? Carbon has 4. 1, 2, 3, 4. Nitrogen has 5. So go 1, 2, 3, 4, 5. Oxygen has 6. 1, 2, 3, 4, 5, 6. Fluorine has 7. 1, 2, 3, 4, 5, 6, 7. And neon has 8. 1, 2, 3, 4, 5, 6, 7, 8. Now, what we're looking for to tell us how many bonds an atom wants to make is how many unpaired electrons we see in its Lewis dot symbol. Boron has 3 unpaired electrons, so it wants to make 3 bonds. Carbon has 4 unpaired electrons, it wants to make 4 bonds. Nitrogen has 3 bonds. Oxygen has 2 bonds. Fluorine has 1, so it wants to make 1 bond. Neon has no unpaired electrons, so no bonds. It's a noble gas. 8's the magic number. Okay, everybody else is trying to look like neon. Carbon, nitrogen, oxygen, fluorine, they all want to look like neon. And they're representatives of their family. So chlorine, bromine, iodine are all going to behave like fluorine and want to make 1 bond. Oxygen, sulfur, selenium all want to make 2. Nitrogen, phosphorus, arsenic want to make 3. Carbon, silicon want to make 2. Boron, poor little boron, we'll talk more about him. He can only make 3. And even if he makes 3 bonds, poor carbon, poor boron, he's just out of luck. He can't look like neon. So let's go ahead. Okay. So, I've written it all out in the notes for you. Also, I want to point out hydrogen. Hydrogen only can make 1 bond because hydrogen's outermost shell is the 1s subshell, and it can only hold 2 electrons. So hydrogen's got 1 electron, it can only make 1 bond. Okay? So hydrogen always makes 1 bond. Fluorine and the members of the fluorine family want to make 1 bond. Oxygen family wants to make 2, nitrogen 3, carbon 4, poor boron 3. Fluorine and hydrogen are never then found between 2 other atoms in a compound. They're always going to be found on the outer edge of a molecule. Okay? They're never going to be found in the middle of a molecule. So let's go over how we're going to do a Lewis dot structure for a covalent molecule. And here are the rules. Add up all of the valence electrons for all of the atoms listed in the molecular formula of the covalent compound, or polyatomic ion. If it's a polyatomic ion and it's positively charged, take that many electrons away. If it's negatively charged, add that many electrons to your count. place the element that is furthest to the left and further down, the one that can make the most bonds and is the least electronegative, in the center of the molecule. All other atoms are going to be placed around that, because remember, we're dealing only with molecules that have one central atom and everything hanging off of that. Okay? Remember, hydrogen and fluorine are always what we call terminal atoms. They're always going to be found on the outer edge of the molecule. And then you connect all outer atoms to the central atom by single bonds. Remember, a single bond is 2 electrons. Then we subtract this number of electrons from your total electron count. Give out electron lone pairs, we give outer electrons lone pairs of electrons to complete their octet, except for hydrogen. It doesn't get any more. When it's bonded, it's done. Give any remaining electrons as lone pairs to the central atom, and then you want to check the valence of each atom to make sure that it is complete. If it is not, we'll take lone pairs from an adjacent atom and we'll make a double bond or a triple bond to fix things. But we do not make double or triple bonds until we have given out all of the electrons. Okay? Now, we're going to just try some structures. So I'm going to be drawing. You can leave that just where it is. Okay, guys. We're going to start out with something simple. We're going to start out with CH4. I have one carbon that has 4 valence electrons, and I have 4 hydrogens at 1 valence electron apiece. So we've got 8 valence electrons to build our molecule. Between carbon and hydrogen, carbon's going to go in the middle, because hydrogen is never in the middle. Okay? I'm going to surround it by the hydrogens. Carbon's in the middle, surrounded by hydrogens, and then I'm going to connect everything up with single bonds. 2, 4, 6, 8. So 8 electrons minus 8 electrons, 0 electrons left. Now I look at it. I want to make sure that everybody has a completed valence. This hydrogen sees 2 electrons in the bond. That's a completed valence for hydrogen. So each one of these hydrogens sees 2 electrons, it's good. The carbon sees 2, 4, 6, 8. It reached the magic number of 8. Carbon is good. So this would be the Lewis dot structure for CH4. Okay? Now, let's try ammonia. NH3. Now, nitrogen has 5 valence electrons. So I've got 1 nitrogen at 5 valence electrons. We have 3 hydrogens at 1 apiece. Lo and behold, I get 8 again. Okay? Now between nitrogen and hydrogen, nitrogen goes in the middle. Hydrogen, hydrogen, hydrogen. I connect up 2, 4, 6. So 8 electrons minus 6 electrons. I've got 2 electrons left. They're going to be given as a lone pair of electrons to the nitrogen, minus 2 electrons, 0 electrons left. Now it's time to check. Hydrogen, each hydrogen sees 2 electrons, it's good. The nitrogen sees 2, 4, 6, 8. Nitrogen sees the magic number of 8, we're done. Okay? This pair of electrons is called a lone pair because it's an electron in the atom's valence that's not involved in bonding. Now let's jump it up a little bit. Let's try carbon dioxide. Write that a little higher. So I've got 1 carbon at 4 valence electrons. We've got 2 oxygens at 6 valence electrons apiece. So that's 2 times 6 is 12 plus 4, 16 electrons. Okay, Between carbon and oxygen, carbon is further to the left on the periodic table. Carbon wants to make 4 bonds, oxygen only wants to make 2. So carbon's going to go in the middle. Okay, connect up with single bonds. 2, 4. I've got 12 electrons. I start out by giving lone pairs of electrons to the outer atoms. 2, 4, 6, 8, 10, 12. I have no electrons left. Well, oxygen sees 2, 4, 6, 8. It's fine, 2, 4, 6, 8 for this oxygen, but carbon's only seeing 4 electrons. It's short. I'm not done yet. So what I'm going to do is I'm going to take a lone pair of electrons here and I'm going to make a double bond. So I get this. Okay? Now it's better. This oxygen still sees 2, 4, 6, 8. This oxygen sees 2, 4, 6, 8. The carbon now sees 2, 4, 6, but it's not 8. So I'm going to take a lone pair of electrons here and I'm going to make another double bond. And I get, I get this. Now, this oxygen sees 2, 4, 6, 8. This oxygen sees 2, 4, 6, 8. And the carbon sees 2, 4, 6, 8. Okay? Nature has a tendency to like symmetry. So I'm going to make double bonds on both sides instead of a double bond on one side and a triple bond on the other. Okay? Plus the fact oxygen likes to double bond, it doesn't like to triple bond. Now, as we're doing some of this bonding, just let me remind you from chapter 4, carbon, nitrogen can make double bonds and they can make triple bonds. And they do it with ease. Okay? Oxygen, oxygen, sulfur, silicon, oxygen, sulfur, silicon. Let me think here for a second. Oxygen, sulfur, silicon, phosphorus. These guys can double bond pretty easily. Phosphorus, you can sometimes beat it into triple bonding. It doesn't really like to. Everybody else really wants to stick to single bonds. I can force some other things into forming double bonds, but it's not their first choice. So carbon and nitrogen can double bond and triple bond. Oxygen, sulfur, silicon, phosphorus, you can think about those as double bonding. Everybody else is going to try to stick to single bonds unless they're abused to the point that they have to do something unusual. Okay? Now, let me show you some other examples. Okay, so let's say we had PCl3, phosphorus trichloride. We've got 1 phosphorus and 5 valence electrons. We've got 3 chlorines at 7 apiece. 3 times 7 is 21 plus 5 is 26 electrons. So I'm going to put the phosphorus in the middle and I'm going to put the chlorines around it. Phosphorus is further to the left than chlorine. It can make more bonds. Okay, connect up with single bonds, 2, 4, 6. That leaves us with 20 electrons. I give them out as lone pairs, 2, 4, 6, 8, 10, 12, 14, 16, 18. That leaves us 2 electrons. So they're going to go to the phosphorus as a lone pair. chlorine here sees 2, 4, 6, 8. That one sees 8. That one sees 8. The phosphorus sees 2, 4, 6, 8. Okay? So those are some examples. Now let me show you. Let me show you hydrogen cyanide. Okay? I've got one hydrogen at 1 electron. I've got one carbon at 4 electrons, and I have one nitrogen at 5. 5 and 4 is 9, and one more, that's 10 electrons. Now, carbon is the element that's furthest to the left. Okay, remember, think of hydrogen in this situation as being over fluorine. So carbon's going to go in the middle, hydrogen and nitrogen on either side. Kind of mimics what how the formula is written. Okay, connect up with single bonds, 2, 4. 6 electrons left. Hydrogen's full at 2. I don't give any more to hydrogen, so I'm going to come over here to the nitrogen, 2, 4, 6. No electrons left. Okay? Now, carbon only sees 4. So if I make a double bond, things are better. 2, 4, 6. Nitrogen sees 2, 4, 6, 8. So I'm going to have to make a triple bond. Fold another pair of electrons in. Looks like this. Nitrogen sees 2, 4, 6, 8. Carbon sees 2, 4, 6, 8. Hydrogen sees 2. Okay? So triple bond. And carbon and nitrogen can triple bond. All right, so let's kind of move on and start talking about exceptions. Every rule has exceptions, right? So we're going to look at exceptions to the octet rule. We're going to start out with those that have fewer than 8 electrons around the central atom. Okay? The most common examples of electron deficient molecules, molecules that have fewer than 8 electrons around the central atom, is when you have beryllium and boron. Even though beryllium is a metal, it can sometimes be involved in covalent bonding. So let me show you an example here. Okay? Now, a classic example would be boron trihydride, BH3. Okay, one boron has 3 electrons. We have 3 hydrogens at 1 electron apiece. That's 6 electrons. There's no way to make 8 out of 6. Okay, boron goes in the middle. Single bond it to the 3 hydrogens, that uses up the 6 electrons, there's none left, and there's no way to give boron fission of 8 electrons. There are only 6. Okay, that makes this an electron deficient molecule. And electron deficient molecules are very chemically active. Boron compounds have a tendency to make good contact explosives because they are electron deficient. Boron chemists are usually missing at least 1 finger because in the course of their research they've usually blown off one. They give them corner labs on the top floors with blowout walls and bomb-proof walls between them and the rest of the building, because it's not if they blow up their lab sometime, it's when they blow up their lab. When I was at Indiana, a student was mixing up a reaction in a 10 milliliter beaker in a fume hood behind 2 blast shields, and something went terribly wrong and it blew up and it blew the blast shield through the front of the fume hood shield. So yeah, boron, Okay? It throws temper tantrums because it's electron deficient. Okay? So that's an example of an electron deficient molecule. Now, on top of having electron deficient molecules like boron, we can have what are called the odd electron molecules. And they're called odd electrons because they've got an odd number of valence electrons. So if we looked at something like nitrogen monoxide, the no molecule, I've got one nitrogen at 5 electrons. I've got one oxygen at 6 electrons. I get 11 electrons. Odd number of electrons, that's why it's called an odd electron species. So I've got the nitrogen and oxygen. I first connect up with a single bond. So 11 electrons minus 2 electrons, that gives me 9 electrons. 2, 4, 6, 8, 10, well, excuse me. 2, 4, 6, I'm going to do it oxygen first because it's more electronegative. 2, 4, 6, 8, 9. 0 electrons left. Now, oxygen's fine, 2, 4, 6, 8 here. Nitrogen sees 2, 4, 5. I can make things better by making a double bond. And then I get this. 2, 4, 6, 8 for oxygen, 2, 4, 6, 7 for the nitrogen, and that's as good as it gets. Okay? It's still got an unpaired electron in its valence. This makes it a molecule that we call a free radical. Okay? Free radicals chemically and biologically can be quite dangerous. Free radicals inside your body do damage to other molecules. It's got an unpaired electron. It wants another electron. So it goes and looks for other molecules to attack to try to get an electron. Okay? Your body makes special vesicles inside your cells that go around slurping up free radicals. Hydrogen peroxide does its damage to cells and kills them and will kill viruses because it's a free radical. And because it's that free radical, it actually attacks cell walls and the cell coating of a virus, and that's how it kills things. Okay? So free radicals have a it has an odd number of electrons, and you're going to end up with one electron that is by itself in the valence. Okay? So they're very, very highly reactive. Now, our next category of exceptions to the octet rule are the expanded valence molecules. Okay? Molecules in atoms in the third period or larger period. So on the third row, the fourth row, the fifth row, the sixth row, the seventh row, can have an expanded valence, in some cases up to 12 electrons given the right circumstance. So they can have an expanded valence. Okay? So some examples would be something like sulfur sulfur hexafluoride. So I've got one sulfur at 6 electrons. I have 6 fluorines at 7 apiece. So 6 times 7 is 42, plus another 6 would be 48 electrons. Okay, sulfur's in the middle. The fluorines are going to be spread out around the sulfur. Remember, we've got single central atom molecules, and a fluorine can never be between 2 other atoms. We connect up 2, 4, 6, 8, 10, 12. That leaves me with 36 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. Okay, and there we go. Now when we look at sulfur, it sees 2, 4, 6, 8, 10, 12. Sulfur is displaying a expanded valence. Okay? To have an expanded valence, the outermost shell of the atom has to have the empty D subshell. And you have to get to that third period where the outermost shell is the third shell to have that empty D subshell sitting there to expand out to bond. All right? Some other examples would be things like xenon difluoride. Let's go. Xenon is a noble gas. It starts out with 8 valence electrons. Xenon, though, is a big enough atom that if you beat the crap out of it, you can make it bond. Even though it's going, I'm a noble gas, I don't like to bond. Okay, so we have one xenon at 8 electrons. We have 2 fluorines at 7 electrons apiece. So 2 times 7 is 14. So that's 22 electrons. Okay, xenon's going to go in the middle. Fluorine, fluorine. 2, 4. So that's 18. 2, 4, 6, 8, 10, 12. I have 6 electrons left. Any electrons that are left at this point go to the central atom as pairs. 2, 4, 6. So xenon sees 2, 4, 6, 8, 10 electrons. It's showing an expanded valence. It's made 2 bonds and it has 3 lone pairs. Okay? So that's another example of an expanded valence. Now, we're going to be working on our Vesper lab, and the first thing that you're going to do in your Vesper lab is we're going to draw some of these Lewis dot structures, and you're going to get practice, okay? And just to make sure that everybody's ready for that lab, let me show you a polyatomic ion, because I haven't showed you an example of a polyatomic ion yet. So let's look at the carbonate ion. CO3 2 minus. Okay? I've got 1 carbon at 4 electrons. I've got 3 oxygens at 6. So 3 times 6 is 18 plus 4, that's 22 electrons. And I'm going to add 2 more electrons to bring it to 24 electrons because it's got a 2 minus charge. That tells us we've got 2 extra electrons for the molecule. Carbon's going to go in the middle, oxygen, oxygen, oxygen. Okay, connect up with single bonds, 2, 4, 6. That's 18 electrons left. 2, 4, 6, 8, 10, 12, 14, 16, 18. 0 electrons left. Oxygens are all fine at 8. The carbon is sitting here at 6. So I need to make a double bond. Doesn't matter which one I do the double bond with. So I get something that looks like this. Now carbon sees 2, 4, 6, 8. Now because this is a polyatomic ion, when we're done, we're going to put brackets around it and we're going to put that 2 minus charge outside. So that when somebody looks at it, they know that we're looking at a Lewis dot structure for a polyatomic ion. Okay? So that's important. All right, guys, I'm going to stop right there for lecture number 1 in chapter 5.